is the Hong Park. Please start.
Thank you. My pleasure to introduce the speaker today, the Cheolhee Han. Actually, he was here in June this year, and this is his second visit at the PCS. He completed his PhD at the KAIST in 2018, and stayed there, the same place, 2 years more as a postdoc, and then moved to the Tel Aviv University. The group of Professor Iran Salah, and he has been worked there since 2020, and his main research interest is the quantum correlation, like entanglement and the coherence, and how to measure these correlations in the metroscopic systems. And now he will talk about the measuring entanglement in the condensed matter system at the finite temperature. He has been here since a month ago, and will stay here till middle in December. And so please contact him at any time when he is available. And yeah, let's welcome the speaker.
Good. Hey, my name is Cheolhee Han, and today I'm going to talk about measuring entanglement in condensed matter system at finite temperature. And in fact, as a theorist, I never measure it, and I just want to talk about some relation between entanglement and measurable quantities. In fact, it's not conventional entanglement; it's entanglement-related things. I will explain. Okay. First, let's start. Very good. Just 5 minutes ago.
Oh, we did.
Okay, so I will start with introducing the quantum entanglement. Maybe most of you don't know about this, but quantum entanglement is genuine non-local quantum correlation. And if you have some system, and then you can bipartite this like A and B, and then to understand the entanglement, we first define the system is separable or not. Separable state is simply the state simply written in this way. It's written in this way. And the entangled state is defined as not separable state. So just if the state cannot express in this way, then we call this as entangled state. Then the natural question is that this kind of correlation, can we quantify these correlations or not? For example, consider pure state and two-spin state like this. This one is separable and obviously not entangled. And this one is spin singlet, which is maximally entangled. And then in the middle, in this state is not separable and not maximally entangled when A and B is not equals to the 1 over square root. Then how can you quantify the entanglement of this state psi prime? To understand this, we first understand the distillation and dilutions. And distillation and dilution is that distillation, if we have R copies of the target system, psi prime, then we transform this state using local operation and classical communications to the approximate Bell state or spin singlet state. And how many states can we obtain? This is the distillation operation. And dilution operation now. This one. Dilution operation is that if you have m copies of a bare state or singlet, then using local operation and classical communication, we transform this state to q copies of this target state. Then the ratio between the n divided by r or m divided by q is some kind of measure. It means that if you have r copies of this state, then how can you make this maximally entangled? How many maximally entangled pair can you make, or vice versa? And interestingly, the ratio between this or n divided by r or m divided by q is the same when the odd number goes to infinity, and this ratio is the same as this entanglement entropy. So we can
one question. This the dilution process, that if you have some target state,
yes.
then can you find some corresponding maximally entangled stage? Is it uniquely determined?
Yes, in fact, this process is also my understanding is explicitly proved for spin singlet, as two spin pure state case. And also my understanding, we can easily define there is a maximally entangled state like singlet or singlet-like state for general systems. So because of these things, we can say entanglement entropy quantifies the entanglement of the pure state. But for mixed state, there is it's a bit difficult because entanglement entropy cannot quantify the entanglement in the mixed state because this quantifies some kind of Sommer or classical correlations. So they cannot quantify properly. They cannot quantify entanglement in the mixed state properly. And
sorry.
Yeah.
One question before.
Yeah.
What is the local correlation and classical communication procedure that you use to distinguish the states in the previous slide?
Local operation and classical communication.
Yeah.
Local operation is that you can measure it. You can measure, for example, if we have m copies of this kind of spin systems, and then you can unitary transform of this A system or B system, vice versa, or you can measure A system or B system. And you can tell, okay, if you measure the A system, then you can tell the result of the measurement to the B part or bar or something. So this is a local operation and local unitary or local measurement or something. And classical communication is that they know the result, that they know the result of the operations. This the ROCC. This the meaning of the ROCC.
Maybe you can, I don't get it yet. So what would be non-local as compared to local in that?
Non-local means that if you unitary evolve these both state, then it is non-local. Or if you measure the up or down state as a projection measurement of up or down measurement, then it is non-local. If you only operate on one side or one part, it's okay. It's local.
Classical communication means that someone measured that.
Louder, please.
Third part. Classical communication means that one experiment is measured it and sent this information to the other one, and the other one didn't measure it.
Yeah. That's what I understood. Okay, so mixed state is a bit difficult because this kind of distillation operations or dilution operation is also very, very difficult for general mixed state. And only things we know about the entanglement in the mixed state is this thing. It is therefore the separable state by definition, and it is maximum for maximally entangled state like spin singlet, and it is not increasing under local operations and classical communications. because the definition of entanglement is non-local and constant. That's why it is not increasing under the local operation and classical communications. And if there is some quantity O which satisfies the above three conditions, then we call this O as an entanglement monotone. And we say that this quantity quantifies the entanglement of this mixed state. And one popular example of entanglement monotone is the negativity. Negativity is related to the partial transpose of density matrix. And if density matrix is separable, then the partial transpose density matrix also, partial transpose density matrix gives only positive eigenvalues. And if it is entangled, then it's not the equivalent, and if it is entangled, then it gives negative eigenvalues. And
sorry,
yeah.
the question, why is the quantity is 0 for separable states?
This is by definition, because entanglement is 0 for separable state.
Yes, and you put this form to your definition, this entanglement entropy, then
it is 0.
it's 0.
But entanglement entropy, if this law A has some complicated structure, then it is not. It can be finite value. That's why it is hard to quantify entanglement in mixed state using entanglement entropy. Okay, so negativity, but you can see this negativity has this kind of absolute value of this partial transpose density matrix. So it is highly nonlinear in density matrix. So it is generally hard to measure. And for the measurement point of view, people use simpler versions, which is called the Renyi moments of this kind of monotone. For example, for entanglement entropy, we can write this and this Renyi moments like this way, and the negativity is also this way. This Renyi moment is much simpler because there is no this kind of absolute value or log or something, just simple power law, just a simple power. But unfortunately, this Renyi moments has many similar properties, but it can increase under this local operation and classical communications. There is some counterexamples that, so it's not a true entanglement monotone, but it can capture something.
Sorry, here what is alpha?
Alpha is some number, 1, 2, or 1.5 or something.
Exponent.
It's just some exponent.
Exponent.
Alpha is exponent of this density matrix.
You can choose the arbitrary value.
Yeah, but for people generally use alpha as 1 or 2 or 3 or something. Not 1 or 2 or 3 or something. 1 is special.
Can I ask you about, so if I understand correctly, if you take this entropy, this entanglement entropy, then and you do any local operation, so if you have not a maximal entangled state, but some entangled state, and then you say local operations as you defined local, then this will not lead to an increase of the entanglement entropy of
yes,
not increasing under local operation means what? What is not increasing?
This quantity, some entanglement is not increasing under local operations.
Can it decrease?
It remains same or decrease. Usually decrease.
Is it because local operations and classical communications make the does it destroy the state?
Entangled state.
Yeah.
Usually, not always, but because we can choose many kind of operation which remains the entanglement the same, which makes the entanglement just the same, not changing. I mean that all of this local operation or classical communication destroy entanglement. Something remains the same. Something makes it remain the same.
I'm not sure, but the state is destroyed, but then the entanglement entropy is still the
Oh, no,
same.
no. Sorry, maybe I didn't understand the question. So, not, yeah, if, as you said, if this local operation or classical communication destroy the state, then entanglement goes to decrease or goes to zero or something.
And the local operation here, it need to be unitary or not.
Unitary or not non-unitary, like measurement. Measurement can be operation. Okay, now we move on. So there is many approaches to derive
So
measurement.
I still have a question for this because if I can have any operator,
Yeah.
then for example, if I have if I have not maximum entangled state,
Yes.
but I can apply the operators that not unitary only on single, like on A qubit, I can make this entangled, right? Because I do not require to be unitary.
Sorry, I didn't hear you.
So I can have the initial state
Yes.
so that it's not maximum entangled.
Yeah.
But I can apply the local operator. That means I only apply operator on the first qubit.
Yes.
At the end, I can make it like higher entangled. So basically, entropy can be like increase or decrease, right?
Yeah, usually decrease or remains the same, and usually decrease.
But I think that the question is that the non-unitary operation to some qubit A,
Yes.
for example, could increase the entanglement entropy by transforming some not maximally entangled stage to the maximally entangled state.
So for example, if I have like up A down B and with the plus sign,
Yes.
down A up B.
Yes.
But now if I have the non-unitary operator such that I switch the side of the down, but I keep the side of the up,
Yeah.
I will go to the maximum entanglement. So this operator, if I allow that, it's not unitary, but if I allow to do this.
So this is the unitary, or this is the local operation. That's I'm not sure, because local operation, optimal understanding, it looks like you measure you change you want to do some kind of control Z operation.
I just like change the side of the first spin.
Yes.
If the up, I do not do anything, and down, I multiply by a minus sign. So from the up down plus, I will go to the up down plus down up, I will go to the up down and minus.
Yeah, then you mean that if we choose this A side spin up, and if this is up, then you remain the same.
Yeah.
And if it is down, and you want to flip.
I change the side only. I multiply by
Side.
flip the side.
But that's not a unitary operation.
It's unitary. Yeah,
It's unitary.
it's unitary. It's sigma z.
Sigma Z. Change the sign.
And so from the state,
Remains the same entanglement, right?
No, we change it because you started from, let's say you started from a non.
Yeah, so you mean that if it is A and B and plus, then you can see. But in that case, the entanglement in this is because this is pure state. You can use the entanglement entropy, and in that case, entanglement entropy remains the same, I think, because only sign changes that. Then the reduced density matrix must be A square and B square something. So I think entanglement entropy remains the same.
I think the form you suggested is the unitary operation doesn't change the entanglement.
Some unitary operation doesn't change the entanglement. Some other unitary operation can change the entanglement, and this change always decrease.
It doesn't make sense to me, frankly speaking, because I can always invert the unitary operation, right? So I can always start from the end kind of go back
Yeah.
with the inverse of a unitary operation, and then what? Then apparently I should increase entanglement or what?
Yeah, not 100%, but I think if you have only these two spin states, I think this single unitary cannot change the entanglement. But if you have larger system, then it can change, maybe. So, but yeah, this is in the, in fact, this statements are in the textbook of the quantum information. So I understand. Maybe we can discuss more later. Okay.
May I also ask?
Yes.
This n depends on alpha.
This and what's the n?
Yeah.
Depends on alpha. Yeah.
So in principle, these are different quantities.
Yeah, different alpha and different quantity.
Yeah. Now, how are you going to use them? And maybe dependence on alpha is carries some information about.
Yes. People believe it, but people did not develop much. So people say so for the negativity case or entanglement entropy case, second or third Renyi moments of this quantity gives entanglement information, but people do not strictly quantify. It's a difficult question. So I understand I think I understand your question, your point, but people do not understand this well, the dependence of alpha well. Okay. So, question?
Yeah, is there anything that is easy to compute for mixed states? Any measure?
This negativity is, I think, up to my understanding, is the easiest quantity to measure, because other quantity there's many other entanglement monotone, like entanglement formation or something, but you know
that is impossible. Sorry.
Yeah, maybe you know that they consider infimum or some. I don't know very well, but yeah.
Got it. Thanks.
Yeah. So there is many approaches. There are many approaches to measure entanglement, mainly Renyi moments of these monotones in the synthetic system. Synthetic system means that cold atom systems or some kind of condensed matter systems, and they use copies of the system and make them interference between the two copies and measure it, or they use kind of random measurement. Random measurement means that if they have some systems and they choose part of the system and they evolve it randomly and then projectively measure and measure and collect the data, and after doing many times and using some statistical averaging, they obtain some kind of quantum average. But you can see that in this experiment, they only consider a 4-side system, and in this experiment, they only consider kind of 20-side system or something. So up to now, there is no practical experiment or no practical proposals to measure the entanglement, at least the Renyi moments of this entanglement for a condensed matter system, which has much more than this 20 outside. So I wanna before I show the relation between the measurable quantities and the entanglement, I want to introduce a new kind of quantum correlation, which is called this symmetric separability. Consider a system has some kind of symmetry. For example, this density matrix is commute with some kind of charge. Then this density matrix has block structures like this. This block corresponds to the density matrix with under fixed charge n equals n is n prime or n is n prime plus 1 or something. Then assume that this density matrix is separable. Then does it mean that all of this block diagonal structure is separable or not? And the answer is not always. Sometimes yes, or sometimes not. So we can define a new kind of separability. It is a bit more strict. the density matrix is separable, and this separable density matrix or this separable density matrix conserves the charge. Then this density matrix is written in the sum of separable and conserves of charge, conserving this symmetry. So we call this as a symmetric separable state. And we want to quantify this kind of inseparability, using similar strategy of entanglement. And to do this, I first introduce a quantity which we call number entanglement entropy, which is the entropy difference between the original density matrix and this new density matrix rho m. And this rho m is the density matrix after measuring some subsystem charge NA. And it can be written in this way. It's this large pi NA is the projection operator that projects the state. It has a subsystem charge NA equals to some value.
So previously you had the conservation of the total charge, but now you want to project to the conservation of the charge with the subsystem.
Yes, yes. So this quantity is so this law, we only consider that this law conserves some charge, and we can. I will show that. Not show. Sorry, it's shown in this paper. But this quantity has some meaning, like monotonic meaning. I will explain. Consider this double quantum dot system. For Hamiltonian is this way, and for summer density matrix, if the Hamiltonian conserves the charge and density matrix also conserves the charge, and the density matrix has this kind of block structure, and in this case, this rho m is simply kill this off diagonal element of this subblock blocks of the density matrix, and then for the ground state, you can obtain the delta S for number entanglement entropy is log 2.
Sorry, one question. This n is the total.
In this case, total particle number, but we can choose this n is a kind of total spin or something. Here,
Just confused. Why the off diagonal is the matrix rho m should be.
Because here this is a projection operator of subsystem charge.
I see.
So it's a cancel 1, 0 and 1, so it's off diagonal kills them. Only diagonal remains. An interesting point is that it is not increasing under symmetric RCC. Symmetric RCC means that if the initial density matrix conserves some charge, then after this RCC operation, then it also conserves the charge. Then you call this RCC operation as a symmetric RCC operation. And this quantity is 0 for symmetric separable state, as I defined. So we call this quantity as a symmetric entanglement monotone, which is not a true entanglement monotone, but similar to the entanglement monotone. Then the last question, the last and final question is that is it measurable or not? And
What do you mean by symmetric?
Symmetry means that this is just a naming, and we say it's symmetric because it conserves some charge. It is a symmetry related separability, so we call this as just a symmetric entanglement. What's your question precisely?
Yeah, what is symmetric in this case?
In this case, we only consider the symmetric system has some kind of conservation charge or conservation spin or something. So that's why I call this as a symmetric something, symmetric, and everything looks like entanglement, as I said before. That's why.
What happens if the system has more than one symmetry?
Good questions, and we mostly focused on the simple system that's only some kind of U1 charge symmetry or spin symmetry. But if we have one more charge, then maybe this rho m must be differently defined. I'm not sure. We didn't think about it deeply. Thank you.
His measurement is work in the spontaneous symmetry, right?
Spontaneous symmetry. In fact, I didn't think about it.
But the symmetry exists for states not follow the symmetry sometimes.
Yes, I understand.
It's a Hamiltonian symmetry or state symmetry.
Frankly speaking, I didn't think about this deeply. I discussed it, but there's no meaningful feature in these directions. So okay, so the main point of this talk is now here. To measure this thing, I first defined the Renyi moments of this delta S or number entanglement entropy in this way. This is just a low, since it is defined as entropy of original state and measure the density matrix state. We can write this Renyi moments in this way: the trace of rho m of alpha and trace of rho of alpha. And here I consider the summer state whose density matrix is written in this way. And here I choose this subsystem A as only two states. NA, for example, NA equals 0 or 1, or for spin is up or down or something. And I choose NA equals 0 or 1. And in this case, this projection operator becomes dramatically simple. NA equals just projection of NA equals 1 is just NA, and projection of NA equals 0 is just 1 minus NA. Then we can rewrite this second Renyi moment in this way. Then this trace of rho m square is simply in this form, and the trace of rho square is simple. Although it looks a bit complicated, maybe you can find this part is quite similar to the imaginary time correlators. For example, imaginary time correlator of 2-point imaginary time 2-point correlators of NA is written in this form, and you can put the proper time 1 over t and some temperature which is t divided by 2. Then you obtain this form, and you can see this is the same as this trace. So we can rewrite this second Renyi moments of this number entanglement entropy using this these 2-point charge correlators, imaginary charge correlators. So using some analytic continuation, we can rewrite this second Renyi moments of number entanglement entropy in terms of occupation and some charge susceptibility. And the interesting point is that this is to measure the second Renyi moments at temperature T, we need to measure the number and charge susceptibility at T divided by 2. This is because we use some kind of properties of equilibrium physics. And it is applicable for spin 1/2 system or qubit system and spinless charge quantum dot system, which is only 2 states, 0 or 1. And here I use the strategy that we can see the density matrix and the time evolution operator is governed by the same operator, Hamiltonian. And these strategies can be generalized to other quantities such as negativity. So using this, we can write the negativity of some alpha in this form, maybe slightly more complicated. And it is useful for measuring entanglement between qubit versus environment or impurity spin versus space.
So basically from Z, you can measure locally only on A, right?
Yeah, this local site and measure the charge or measure some measure difficult, but measuring charges might be possible.
Okay. So one question: is the local measurement what comments on the time scale? Is it important?
That's in fact that's a good question. Because there is integration of omega. This integration of omega is quite important. So it means that this omega must be very small to very large. So it means that the time scale must be very small to very large. And the short time scale is, for my understanding, is a bit hard to measure. It means that the large frequency limit is hard to measure.
So measure the local NA should be easy, but measure the correlation.
Measuring this is super easy, and this is
how you measure the quantum correlation.
For me, theoretically I know some formula, but when I talk to experimentalists, and they said that it's almost impossible.
Yeah.
But only possible for the almost classical system. It means that tunneling is very small, then we can measure it. Tunneling is larger, then maybe you cannot capture the difference. But you know that rather than this form is much more global. That's what I thought.
I think if you think about some dissipation.
Dissipation effect in this measurement.
This experiments, narrow experiments relate to this.
Yes.
This correlation.
Yeah, but here I assume that the density matrix must be summer density matrix, so I assume that there is no dissipation. I will think about it. Yeah, I agree. But I will think about it.
I want to understand when you speak about temperature.
Yes.
Is it temperature of the environment, or you assume that your system is actually at the equilibrium?
I assume the systems are always in the equilibrium because,
But then, what is the meaning of entanglement? Because at the equilibrium, we know that all states there is a partition in the equilibrium. And that's why all states just come with their energy, and that's it.
Sorry, maybe I don't understand the question.
I thought that entanglement is, in a sense, a way to understand how a system is. The degree at which system is out of equilibrium. Because
entanglement is meaningful in equilibrium also.
It is, but in the equilibrium you have not one particular state, but many of them.
Yes, of course.
And states are entering this sum only depending on their energy.
Yes,
all phases have only relaxed.
Yeah, but not always. That if there is some tunneling between the two levels, if you consider double quantum dot, then if you turn on the temperature, then it remains the entanglement or negativity remains not same, similar as some temperature, and it goes to decay faster. It is not just if you turn on the temperature, then it goes down so suddenly. It is not the thing.
Okay,
maybe you can discuss later. Yeah. Thank you. So here I want to. So okay, it is useful to measure the entanglement in the impurity spin system. So I will explain about multi-channel Kondo examples. It is kind of a simplest, not the simplest. It's one of the famous exotic impurity model, which is that the impurity spin interact with many leads, in this case, two leads. And there is a magnetic field on the impurity. And it is demonstrated in many experiments using some spin channel Kondo system or charge Kondo systems. And there appears many exotic physics. They predict that there is some kind of fractional excitations like Majorana-Germos in the two-channel Kondo system, and there appears Fermi liquid to non-Fermi liquid crossovers. And at the ground state, at magnetic field equals to 0, then this ground state looks like a maximally entangled state. So it is known that the negativity and delta S I computed is log 2 at 0 temperature. And maximally entangled between the impurity and the or other bases. So in this case, negativity and delta S between this impurity and or the bases is just log 2, independent of number of channels. And now I'm exploring the temperature correction of this entanglement. Okay, I computed the one channel and two channel case without magnetic field. I used mainly homogenization and differentiation technique. And you can see for one channel and two channel, they show quite different temperature scale, temperature dependence. And to understand this further, we plotted this log plot. And we find that for one channel Kondo, the temperature scaling proportional to the T square, which is the signature of Fermi liquid. And for two channel Kondo, it shows the T linear behavior, which is the properties of non-Fermi liquid. And for general M channel Kondo case, this arbitrary moment or arbitrary R-path moments of this delta S is simply depends on the temperature with same scaling. This delta M depends on this number of channels. And this coincides with known measures for the negativity or entanglement relations. And if you apply some kind of channel symmetry, then you can see there appears a crossover between Fermi liquid or one channel Kondo system to two channel Kondo system. You can see it initially behaves as a T square, finally it behaves as T linear. You can capture, this captures the crossover. And more important thing is that when we apply magnetic field, then the ground state is simply spin down or up state because the effective interaction strength becomes weaker. Then there is kind of phase diagram. This is phase diagram of H versus temperature. And you can see for the load, this is this kind of plot. This blue one is a no magnetic field case, and this sky one is the highest magnetic field. And you can see delta S is increasing as T increasing. You can see the entropy is increasing as temperature increases as for the low temperature. This is, for me, it's a bit counterintuitive because I initially thought that usually entropy entanglement decreases as temperature increases. But in this case, this is the signature of this Fermi liquid to non-Fermi liquid crossover because this Fermi liquid is localized moment phase, so it is spin is just decoupled to the lead. And when we apply some finite temperature, then it goes to two channel Kondo again. And for one channel Kondo case, this delta S does not show this kind of non-monotonic behavior. It monotonically decreases as temperature increases. So this captures signatures of non-Fermi liquid. That's interesting way. So, okay, this is a summary of this talk. So I introduce some kind of quantum correlation, which is called the symmetric entanglement. And we introduce the delta S, and there's number entanglement entropy. And I claim that this delta S2 between the one qubit or some quantum dot versus environment is measurable using this identity. And this scheme is that using time evolution to extract the finite equilibrium density matrix is general for measuring quantities which is nonlinear in density matrix. For example, it is applicable for negativity easily. So thank you for listening.
One question. Should comment more about the slight increase of this entropy in the Fermi liquid waste? Why
Yes, because in this Fermi liquid limit is simply magnetic field dominated region. So magnetic field dominated the physics, so it means that spin goes or spin choose one direction, like down. Then the interaction between the bass becomes weaker, effectively weaker. So then this is decoupled to the lead effectively. Then the entanglement becomes down. Entanglement goes down.
With the coupling weaker as you increase the temperature?
No, the coupling itself is not decreased, but effectively its effect is decreased. Because this magnetic field is relevant. There is a kind of crossover.
About the process of
Here I assume that the impurity site has only 2 degrees of freedom. If you have more, then if we consider more site, then we need to generalize this expression. It becomes
general is the probability of the application.
usually not. But channel means that just it interact with this impurity interact with multi channels. It still remains a one spin up or down.
But the virtually change. It is
Virtually,
average is right.
yeah, virtually change it, but I just compute the effective model. So I think you are.
Probability is also related to the improvement.
Sorry?
This is change the conservation.
But effectively, it's not. Yeah.
You showed this nice picture here on the left-hand side.
Yes.
Do you in general have some intuitions that if you have some kind of a phase transition, then you will have some this peak in your entanglement entropy in general? Not only in Kondo problem, but in various problems.
Unfortunately, you might know that this is just one site versus the other, so we cannot capture some kind of phase transition. So only crossover. And in fact, that's very interesting direction, but I don't have any intuition on this direction. Thank you.
Can you comment on the qualitative or quantitative difference between your probe and symmetry resolved entanglement?
This quantity is quite closely related with the symmetry resolved entanglement. Maybe we need to just like if I write the density matrix is in the block diagonal form. Symmetry resolved entanglement is entanglement of this thing. And the quantity I said, the number entanglement entropy is there's a relation, I forgot that. But for pure state, there is a simple relation. Just the number entanglement entropy is just simply n log n. Because right, maybe right. For all of n. So, and this is a probability of you wanna So symmetry resolved entanglement is just entanglement of this thing, but you do it after normalizing. But the probability for this block is just the kind of P of n. Then entanglement, this number entanglement entropy or zero temperature pure state is P n log P n. That's what I'm saying. Or n. This is my delta S, and entropy of symmetry resolved one is just entropy of this normalized block. So there is a relation, not very simple, but yeah, truly.
And in your model, you have J1 equal to J2, is this correct?
Sorry?
In your model, you have J1 and J2 equal.
Yeah, in this, usually equal, and I only have only one figure that this is not equal, then there is a crossover.
So basically, when it equal, then basically you have some kind of linear combination such that you have effectively two different J.
Yes.
You have like Kondo temperature for two different J.
Yes,
And
yes.
at some points that it disconnected and have one channel, right?
Yeah.
Okay.
More questions? If there is no more questions,
Some to learn something to take home, to have some home takes, to have some take home message maybe. For example, we all know that in condensed matter physics, we can have a lot of understanding of a system by measuring like heat capacitance, resistivity, like this quantity. What if I have my sample and then I start to measure my entanglement entropy? What can I learn from this measurement? In the simple words, maybe.
So you mean entanglement is that kind of quantity also gives the information of this density matrix or subsystem. Density matrix is the system, but entanglement is yes, that's a bit difficult to answer, but entanglement is a bit different correlation. It's not just transport or something. So maybe it's not a good answer, but
I think that your supervisor has the idea to measure the Mazurana using entropy, right?
Yeah. So entanglement is that people say is that it is more, it shows more quantumness. So it's kind of rhetoric, but yes. What's the mean field?
The singlet. Use the singlet, but it's not the only thing.
What's the mean field treatment?
You solve the S dot S, sigma dot S.
I use Bougeonization and deformalization. It's not a mean field, simple mean field. It's some kind of special point. It's a kind of Swiss spot. I only saw Swiss spot, not use mean field, but Swiss spot.
If there is no more question, thanks again.